Over the past year, one of the most annoying things in the AI world has been the endless wave of buzzwords. Agent harness, MCP, function calling, React, CLIs, like one term barely settles, and boom, another pops up. It gets tiring, right? At some point, you may not even want to learn what these words mean anymore. But if you ignore them just because you are tired of the hype, you might miss something truly useful. And here's the trick. These buzzwords, they are like road signs. Once you understand what they are pointing to, they show you the fastest path to understanding agents. So today, we're not memorizing jargon, even if you've got no technical background. By the end, you'll get all of them. Alright, let's begin. So first up, let's break down a large language model, an LLM. Everything we'll talk about later, no matter how fancy, is basically doing one of two things, expanding what the LLM can do or making up for what it can't. Now we just call it model. For a model, the only thing we really need to know is how it works. It's basically a text autocomplete game. You see how are you? The model processes the input and predicts what word should come next. For example, am. Here's the key part. After the model outputs am, it doesn't stop. It takes am, adds it back to the end of your input, and uses that new input to predict the next word, maybe doing. Then it adds doing back and predicts again, maybe well. At that point, the model predicts a special end marker, which tells the system to stop generating. That's basically how it outputs. But here's the thing, in reality, the model doesn't actually handle words, it handles numbers, because at its core, it is a mathematical function, so we've got a translator in the middle. Now, if you see how are you, this sentence goes to the translator, which turns the text into numbers. And there are two steps. First is split the text into the smallest pieces the model works with. These pieces are called tokens. Second, the translator maps each token to the number, because the model only understands numbers. That number is called a token ID, and this step is called mapping. After these two steps, the original sentence becomes a sequence of numbers. We call this encoding. Then the translator sends that sequence of numbers to the model. After computation, the model outputs a token ID. The translator then turns that ID back into the text token. This step is called decoding. And that is how we get the first token of the model's answer, 8. By the way, this translator is called tokenizer. Then, the same process repeats for every following token. So you see the pattern? The model reads a sequence of tokens and generates its answer one token at a time. Some words are single token, such as hi, for, and apple. Some may split into multiple, like helpful may be split into help and full. Unbelievable may be split into un, bell, and evable. As a rough rule, one English word is usually about 1.3 tokens. Now this point matters. Tokens are all the model works with. Keep that in mind. It is crucial for understanding everything about agents later. Now let's treat its output as text. Say I ask the model something, and it replies. But when I follow up, it suddenly loses track. Why? Because the model has no real memory. All it can do is receive input and produce output. Every time you talk to it, it's like a brand new interaction. So what can we do? We can give it all the relevant info. But obviously, this is tiring. So is there any easier way? We let a program do it. Instead of sending our message directly to the model, we send it to a program. This program combines what you just said with what happened before, then sends the full package to the model. Now I don't need to do that work myself. Let's call this program the agent program. In fact, you're never talking directly to a raw model. There's always an agent program in between. Now what you see is called the prompt, or more precisely, the user prompt. And all the info the program sends to the model, including the prompt, is called the context. And this approach gives us an extra benefit. Since the model cannot remember things or act alone, the agent program can also connect tools, like a read file tool or a web search tool. These tools are basically small programs. You don't need to know how they are implemented. You only need to know that if you give a tool a clear input, it can perform a specific action and return a result. So when needed, the model can tell the program to call it. Suppose the user asks, how's the weather today? Now the agent program doesn't just pass on the question, it also lets the model know what tools are available. The model's like, alright, I need weather info, and there's a search tool. So the model sends an instruction to call a tool. Then the program calls the web search tool and returns the weather results to the model. After receiving the result, the model composes the answer back to the user through the program. So basically, the agent program is doing the heavy lifting in the background, pulling context together, fetching info. You might have heard of function calling. Well, now that's clear. That's just the model telling the agent, hey, call this tool. But instead of using messy plain language, it sends a clean structured format like JSON. That makes it super easy for the program to quickly know which tool, like web search, and what exactly query, like New York weather today. And program will also return the result in a structured format. But remember, the model has no memory, so the agent doesn't just send back that result, it downloads everything. The tools, the original question, the model's instruction, and the tool's answer. Here we are only showing the information for the single round. By now you've got a handle on all these concepts. The model, tokens, tokenizers, prompt, context, agent programs, tools, function calling. Pretty simple, right? But did you notice a problem? How did the model know I was in New York? I never actually said that. That means we skipped one crucial thing. One function call solves one problem, but real tasks usually need several steps. And here's the truly powerful part. This system can chain tool calls together. Let's look at an example. Let's say the user asks, is today a good day to wash my car? The model's like, alright, to answer that, I need to know if it's going to rain. But first, I need to know where you are. Oh, there's a location tool. I should request to call it. So the model sends a function calling. The program calls the location tool and gets the user's coordinates. The result comes back. Now the model's like, great, I've got the location. Next, I need the weather for this spot. Oh, there's a weather tool. So the model sends another instruction called the weather tool with these coordinates. The program checks, no rain today. The model's like, awesome, no rain. Now let's find a car wash. There's a tool for local businesses. Let's call that. The program returns the result. There's a car wash just 800 meters away. Now it can finally answer the user. Today it will not rain, so it is a good day to wash your car. There's a car wash about 800 meters away, and that round is complete. Now you can see the difference. It's no longer a single tool call. The model is reasoning, acting, using results, and repeating. This pattern is called react. And the reason the model can do this is because the system we built keeps feeding fresh context back into it. So in a way, the model has gained a kind of autonomous planning. And now we can call this whole setup an agent. In simple terms, the model can think, but it can act. The program can act, but it can think. Put them together, and you've got an agent. No matter how powerful today's agent products look, at the bottom, they all built from these same pieces. But when you try to use this in the real world, the problems begin. At first, the agent program can directly include a few tools such as web search, read file, and calculator. But as the number of the tools grows, the program has more and more things to maintain. What each call is called, what it can do, how authentication works, how to parse arguments, how to parse the return results. And that's a problem. If you want the agent to handle more, you got to connect more tools, but the more tools you add, the more bloated and efficiency the system can get. So how do you keep adding tools without making the agent a bloated mess? You decouple things. You keep only a few cool tools inside the agent program and move all the other tools out into an independent tool service. And guess what? That gives you a bonus. Different agents can call the same tool in the same way. Everyone saves time as long as they follow one standard protocol. And that standard protocol already exists. It's called MCP, or Model Context Protocol. So to get MCP is actually pretty simple. The whole process boils down to two steps: tools list, tools call. When the agent program connects to an MCP server, it first sends a tools list request, basically saying, hey, show me what tools you've got. And the server responds with a list of available tools. Here I just list the tool names. In reality, you'll get details like descriptions or parameters. Once the agent program gets this tool list, it gives to the model. Now suppose the user says, can you check if I'm free tomorrow at 3 p.m? The model gets the message and the tool list and thinks, I should call get calendar. So it tells the agent program. The program then sends a tools call request to the MCP server, specifying the tool, the method, and the argument. In this case, the arguments are just the date and time. If the call works, the MCP server returns results. The program gets the result, give it to the model, and the model produces the final answer, give it to the user through the program. So the heart of MCP is super simple. Tools list finds the tools, and the tools call is responsible for calling tools. But did you notice something? MCP and function calling seems a bit similar. Do they overlap? Nope. Function calling is a model's instruction. It's basically saying I need to use this tool, whether that tool is inside the agent program or on some external server. It doesn't matter to the model. MCP, on the other hand, is just how the agent program talks to that tool server. The model isn't involved in that part, so no conflict. They each do their own job. So here's the big question. If MCP is just between the agent program and the tool server, why now it's called a tool protocol? Why model context protocol? Well, the name isn't about who talks to whom. It's about who it ultimately serves. It serves the model. The tool results are fed back into the model's context, so the model can make smarter decisions with fresh info. And when you pair MCP with React, the system keeps feeding the model updated information, so the model adapts each step as new feedback rolls in. That's the true power of MCP. It's constantly turning the outside world into the context the model can actually use. So tools, they are just a method. Context, that's a goal. Now, that's actually why MCP feels like it's cooling off a bit, while CLI is getting more popular. CLI or command line interface might sound technical, but honestly, it's super simple. Think of it as giving instruction through text. I mean, you can click buttons with the mouse, or you can just type instruction directly. Either way, it's just a different way of operating software. But here's the thing, CLI has been around for decades, and that matters a lot for models. During training, models have seen tons of CLI commands. Code, technical docs, open source repos, you name it. And all that knowledge is baked into the model. So models are naturally great at using CLI commands. MCP, though it's still new, models don't just know it. Every time you have to show the model detailed documentation, and that eats up a lot of models' context window. But if you zoom out, both MCP and CLI are doing the same thing, turning outside info into context the model can use. In that sense, they both belong to what we call context engineering. But now, everyone's talking less about context engineering and more about harness engineering. And honestly, most explanations online make harness sound way too technical, but you really don't need that much detail to get it. The clearest definition we've got right now is from LangChain. Agent equals LLM plus harness. On the surface, that sounds clear, but if you think about it, it's kind of saying nothing. Because if you remove the model, everything else is harness. And we still can't really understand what harness means. Let's put the definition aside for a sec and look at it another way. What can context engineering solve? Isn't harness going to solve exactly that problem? So forget the tech jargon for a second. Let's use a simple example to really get a feel of what harness does. Think of an agent as a brand new employee you just hired. Now you are the boss, right? You ask, what's the room temperature right now? So your employee treats that like a task. I need to find the room temperature. First he thinks, I need a thermometer. But then he finds the thermometer battery is dead. So now he's like, alright, I need a battery. He looks around, can find one, and thinks, okay, I'll go buy one. So he hops in a taxi and heads to a convenience store. But after he gets out of the taxi, he realizes he has no money to pay the driver. So he analyzes the situation and comes up with a brilliant idea. Use the thermometer as collateral for the taxi fare. Now he's finally out of the taxi, he gets a battery, but then it hits him, the thermometer is gone. So he's thinking, alright, I guess I need to buy a new thermometer, but he still doesn't have enough money. Now less capable employee will be stuck, but your employee is pretty smart. He thinks it through and come up with something good. Take out a loan. Eventually he gets that loan, loses the original thermometer, buys a new one, installs the battery, measures the temperature, and finally says, the room is now 24 degrees Celsius. Each little step on its own kind of makes sense, but as a whole, it's completely absurd. And this is exactly what happens when an agent doesn't have enough harness engineering, kind of lose of control. In real work, you'll be worried about someone like that too, right? Someone who hits a problem, doesn't report it, just pushes forward and ends up with an even bigger mess. Now, if that employee asks you for a monthly paycheck, after all that, would you really want to pay it? That's exactly why agent products are now competing on their harness. They're working to make these agents more reliable for real tasks. And to get reliable results, you've got to give it a few things. You need a workable method, like what should it do if the thermometer battery is dead? And you need the right tools, like spare batteries or backup thermometer. And rules and constraints, like any high-risk actions involving deletion, payments, or transactions, need to be confirmed first. Now notice we haven't even touched any technical jargon yet, but you can already see why harness matters. And harness isn't some brand new thing. It's been around since the first agent, back in the prompt engineering days. It was just baked into the prompt. Roles, goals, steps, formats, boundaries, all of that was just giving the model a basic framework to work with. When we moved into the context engineering stage, harness was hidden in how we organize the context, what info to include, what history to keep, which tools to show. All of that shapes how the model makes decisions. But once an agent needs to act continuously, handle failures, manage permissions, and decide when it's done, that's why that was hidden behind prompt and context becomes the agent's most visible main line. So harness doesn't replace prompt or context, it organizes both of them, building a system that lets the agent get the job done properly. In a sense, harness is the operating system for the agent. By now you've got a solid grasp on the big challenges agents faced as they evolved, how those got solved, and even where they are headed next. Now let's wrap it up by quickly recapping the key concepts from this episode. LLM, large language model, it only generates the next token based on context. Token, the smallest unit of text processed by the model. Tokenizer, the component that converts between human-readable text and model-readable tokens. Prompt, the input you give the model this time. It can be a question or an instruction. Context, all the information the model can see in the current round. Agent program, the middle layer connecting the user, the model, and tools. Tool, a small program that can be called through the agent program. Function calling, a standard format for the model to request a tool calls from the program. React, a pattern that lets the model think and act in a loop. Agent, a task execution system made of the model, the main program, and the tools. MCP, a standard protocol that lets the agent connect to external tool services. CLI, command line interface. You can think of it as operating software with text commands. Finally, remember one thing. No matter what new concept appears in the AI world next, they're always trying to solve the same problem. How to help a model that can only generate text actually get things done. Alright, that's it. Thanks for watching, and if you enjoyed this, don't forget to hit that subscribe button. I'll catch you in the next one.